second lecture.
Yes, indeed. Welcome back. All right. So let me continue a little bit on board, and then I'll show you some fun stuff on the computer. So this is the theory. Now, how does it work in practice? So in practice, yes. So what we said, we have a quantum state, one qubit or many qubit, and then we can evolve it, we can transform it by unitary operations, right? So let's look at a simple case where I start from my system initialized in quantum state 0. So if you want, of course, for now, might be quite abstract. If you want some kind of physical understanding, think of you have a particle, which is a ball, and there's a dot at the North Pole on the top, and ket 0 is the particle is in the resting position, right? So it's there with the dot at the top, right? And basically, you want to rotate it, right? Because if I rotate it, the dot will be somewhere else, right? So that would be still on the unit sphere. And the way to rotate it, it's a particle. So the way to excite a particle is to send lasers. You send a laser on it that will excite it or make it move. And the laser is basically a unitary operator. So depending on whether you put it like this or from there, it will rotate it. That's the, yes.
That's quite indistinguishable.
Not rotation, the general phase outside. So what I mean is it will, if I rotate it, it will become the form alpha 0 plus beta 1. There may be some e to the point is the phase, the e to the I theta outside. It will not matter once I measure. So it will be indistinguishable when I measure it because, this has norm 1. Yeah.
Also, we said that points apart. In order to throw a laser at it, you sort of need to know the position of it or its state.
Well, no, you don't know the position. The laser is the operator, but there's no measurement there. Okay. You just rotate it. But you don't measure, right? You just change the position. But if you change the position, somehow it will rotate somewhere else.
Okay.
But I don't measure. There's no measurement here.
Yeah, because I try to think of it as the ant example that you said too, and I was like projecting.
But no, I'm not projecting, right? There's no project. There's no measurement here. I just make it move.
Okay.
I just rotate it. So for the
discrete dynamics here. Sorry.
Use the box. Use the box.
Sorry. Now, so there are two sort of basic operations. One is a transformation, the physical dynamics. I don't know who has it. Do you have a mic? Oh, it was your mic.
Safe distance.
Yeah. So no, I would say to summarize them, there are two kind of operations. You're getting too close. Just stay there. It's fine. No need to because otherwise you cannot answer if you turn it off.
Oh, it's not me. Maybe. Okay. Anyway, so there are two kinds of operations indeed. Yeah. One is
to transformation,
and one is measurement.
And that's it.
Yeah.
No more.
Exactly. One is purely quantum. That's the transformation, and one is to go from quantum to classical, which is the measurement. But that's the only two kind of. Only two kind of operations you can do. Oopsie. Whatever. Thank you. Thank you. So let's see. Ooh, it's louder. So let's see how that works. Let's take an example. So my quantum state always started in the 0 state. It's initialized in the 0 position, right? And then I apply a unitary operator to it. So for example, so let me call this psi 0, right? And psi 1, I know what it is, right? This is like this. I'm modifying, let me write psi 0. I apply some unitary operator to it. So here, again, remember, this is just, this is a vector in C2, and now U is a unitary, in this 2x2 matrix. 2, 2 with complex entries and a unitary. Maybe I should write this a unitary, right? So, and this is 2, 2. Example, the NOT gate. So in fact, quantum unitary transformation are called gates, quantum gates. So the NOT gate, the action of the NOT gate is to flip the qubit. If it's in 0, it will flip it to 1. If it's in 1, it flip it to 0. So this is called X. And so the action of X on 0 is get 1. The action of X on 1, this is 0. I'll let you check that in fact, you have a matrix representation like this. So this is the NOT gate. Not because, same as class 4, I'll flip. So this one is very important. The other one that is important is the Z gate, which is called the phase gate. And the action, Z applied to 0 doesn't do anything, but Z applied to 1 changes the phase, so -1. And again, I'll let you check that this is true. I have a matrix representation 1 - 1 on the diagonal. And there's another one, which is the Y gate, but let me not write it here. The point is the set of identity X, Y, Z. These are called the Pauli gates. I don't want to write the Y because it's just adding notations. The point is any 2x2 unitary matrix, you can decompose it into this set of Pauli gates. Now, we need to look at this what's called quantum diagrams. And at first it looks strange, but actually very handy. So if I look at this operation,
Good, right?
sorry,
The phase gate is a symmetry. I mean,
well,
you just flip the one of it.
so Z applied to 0 gives me 0, Z applied to 1 gives me -1. Symmetry in the sense of
Okay, you
yeah.
Geometrically,
Yeah.
one is you flip and the other is you just.
Yeah. I mean, somehow, whenever you see, and obviously I have a notebook, but it's just, for example, whenever you see any notes and introductory notes on quantum computing by physicists, they like plotting this what's called block sphere, which is the sphere and vectors. I don't know why. I mean, it makes nice pictures. Okay, they're much better with pictures than math people, right? But I don't really. I mean, yes, it's symmetry, but this is true in 2x2. But in fact, the system we're dealing with are n by n or 2 to n 2 by 2 to n. So in some sense, the geometric aspects, I fail to see the importance for quantum computing. I might be missing something, but here, yeah, this is just a rotation onto the other side.
And the Y operator, which was that?
I didn't write it because, yeah, it clutters the notation here. But I have, as I said, I have quite a bit of material. I'll show you some notebooks and all that. I'm happy. I don't know if I have a way of sharing them, or if you're interested, just send me an email, or I don't know if, or I'm happy to share that. It's all there. The Y is just another 2 by 2, which completes the basis, but I won't really use it here, so I don't want to write it. Quantum diagram, that's very important. So the way it's represented, you start your system in 0, and then you apply, so let's say X, like this. Okay, this is very technical. I have my quantum state. I apply the quantum gate. Meaning what? Meaning that here I have a quantum state. In fact, I know exactly what it is, right? It's 1, but it's quantum. There's no measurement. I can add the measurement. This is measurement. And after measurement, it's a double sane, meaning it's classical. After measurement, it has collapsed. It's a classical state. Right. So before the measurement sign, everything is quantum. After the measurement sign, everything is classical. Okay. Yeah. Take the box.
Somebody. Ah, you.
Sorry. In that.
No, but that's the thing. Entanglement has nothing. You can. Einstein called it spooky action at a distance. You can be as far away as you want, so you still have the same effect.
I think that was you.
Yes. What did I? So, what is the measurement symbol there? Is it the 2 lines or?
No. Sorry, this is the measurement symbol.
And what symbol is?
If you ask Antoine, that's a very inverted psi. Right? You call it pi in Greece. Inverted pi. No. No, it's half a circle and a bar.
Thank you.
Something it's this. But it's an operator, right? Okay, so now let's look at the slightly more complicated example, where basically everything we did comes into one place, hopefully. So I talked about the Pauli gates, identity X, Y, Z. Now I want to look at one that is slightly more complicated, but a lot more exciting, which is again called H. H, this one stands for Hadamard. And so the matrix representation is like this. 1, 1, 1, minus 1. So I'll let you check if you apply H to 0, 0 again is 1, 0, right? Just so you remember. And you can do computation. That would be 0 plus 1 over root 2. And H applied to 1 is 0 minus 1 over root 2. Okay, there's nothing very exciting in this computation, obviously. But so of course the quantum circuit would be this. I start the system at 0, I apply H, and okay, I'm not measuring, right? Then I'm just writing the system. Now there's something very interesting about this Hadamard gate, which is if I apply H to 0, I get the quantum state 0 plus 1 over root 2. But this state for us as, I don't know, probabilist, I don't know if I should call myself that, but anyway, as people who like probability, let's say, this is very nice because it means, you know, this corresponds to alpha being 1 over root 2, beta being 1 over root 2. Right, so this is alpha 0 plus beta 1. It means what? It means that after applying the Hadamard gate to the state 0, my new quantum state has equal probability of being in state 0 and in state 1. What? It's in a superposition of two states, but the probability of observing 0 is 1/2. Probability the probability of observing 1 is 1/2. Yeah. Let's look at 2 qubits. Now I have a system with 2 qubits. So this is the quantum diagram version. The math notations, and you'll see why, in fact, this is very handy. So this is what? This is I have 2 states. So I start my system in the tensor product of 0 and 0, 0 and 0. And I apply Hadamard. So tensor product distributes. So this is the same as writing H2, 0, 0. Exactly the same thing. So what's important here is operations that act on each row. These are tensor product. Sorry, I should have done that before. If I have, you know, U1, U2, this corresponds to applying U2, then U1 to 0. These are multiplications. Right, so operations along one row, these are classical matrix multiplications. Across rows, these are tensor products. Right? Okay, so let's do a fun computation. Let's do this. Okay, so this is what this is. Of course, this is the same as H0. Now, tensor product n times. Sorry, of course. Okay, so I know this is 0 plus 1 over root 2. Tensor product n times. This gives me 1 over 2 to the n over 2. And then I have 0 plus 1. Tensor product 0 plus 1. Bum, bum, bum. Zero plus 1, n times. And so, okay, I can write it, right? So that I have zeros and loads of zeros, plus zeros, loads of zeros, 1, plus, you know, you have all of them basically, all the way to 1, 1, 1, 0, plus all the ones. Right. So of course, this is not very pretty. So there's a very handy notation, which is this. This means what? This means that, let's just take an example to make it clear. I is equal to 5. Don't know if I can do this at this time of the day. Phi is what? 5 is 4 plus 1. Yes. Which is 2 to the 2 plus minus, let me use colors. Right, I think. And so then what? Then, that would be 1, 0, 1. So the I here is just the binary decomposition, 1, 0, 1. I think that's correct. 4 plus 1 equals 5. Yes. Okay, but of course this is it's a lot more handy than writing all these ones and so on. Now, what does that mean? It means that, okay, the ket I, or the 1, 0, 0, 0, these somehow are just labels. I mean, these are, the states of the quantum, the individual states of the quantum states, but, whatever they correspond to. We haven't attached a physical reality yet to them, right? Now, the point is they each have probability, they squared, so 1 over 2 to the n, probability of happening. So this is what? This is just a uniform discrete distribution over 2 to the power n points, right? And so it's easy to recognize this. So those of you who've got some white hair, I do a bit. When I started, so that was a long time ago, I was, one of the first tasks I was asked to do was in Excel VBA. I know in modern generation, you have no idea what Excel and VBA are, but I had to simulate a uniform distribution in Excel. Not even VBA, just Excel, right? So that was 2002, 2001. I'm that old, yes. No comment. And you do that with the Excel random number generator, and that was a long time ago, right? This is how much I told you there would be a little bit of Monte Carlo, right? This is how much I know about Monte Carlo. I think it was something like this, where this is 1, this is 0, and then basically, I had something like this. There's a lot more mass at 0, a lot more mass at 1, or the other way around. I can't remember exactly. Okay, that was Excel 20 years ago. I'm sure that it's a lot better now. And of course, but that, classical probability, when you do standard, not even stochastic, but, numerical probability, first thing you learn is how to generate a uniform distribution, which is not easy, right? Because our classical computers are deterministic. But the fundamental point about a quantum computer is a probabilistic device. And in fact, the simplest operation you can do on a quantum computer is this. Is actually to generate a uniform distribution. At least theoretically, in the sense as a quantum state. Of course, then, as we said, if you actually want to compute these probabilities, you have to run the measurement many times, like Monte Carlo and so on. But to generate a quantum state, which is in the uniform superposition of 2 to the power n states, this is in fact the simplest operation you can do on a quantum computer. Because the fundamental difference is your classical computer is deterministic and your quantum computer is a probabilistic device. So let me finish a little bit on the on the board, and then I'll show you on the code and that helps, so that I don't go back and forth. I haven't said anything about entanglement. I saw the definition, the linear algebra part, but let's do it via diagrams. So there's, I mentioned this state before, so let's give that a name, entanglement. So we looked at this state before, which was 1 over root 2, 1, 0, 0, 1. And we proved, actually, that this was fully entangled, right? Meaning I cannot write it as a tensor product of two 1-qubit states, right? So this, I can actually write it like this. Maybe if you want to use colors, just to see really well. This is this one. This is really cool, the colors. Right, so the 0, 0 is the top one, and the 1, 1 is the one at the bottom, right? And the other is 0, 1 and 1, 0. So how do I construct a quantum circuit that creates the state? We said if I want to create, let's go back to just a 1-qubit case. If I want to create this, I know how to do it. I have a physical device. I have a quantum computer, which is able to start the system there. It's able to, I have a physical device, again, think of a laser, that performs this operation on my qubit. And then I can run the experiment many, many times, and I will observe the probability or compute the probabilities. And if I have, there's no entanglement here, so I can also do it for 2 qubits and for many qubits, depending on the quantum computer. So this, we know how to do it. In fact, maybe I should add one thing. We cannot do it for any, if you give me a 1-qubit unitary matrix, unitary operator, we cannot implement any such unitary matrix. We can do most of them, but there's some limitation, physical limitations to the device. Basically, I can do this, but I cannot do the one in between. There's some discretization capabilities. So this, we know how to do it. How do I do this? Ooh, this is fun. How do I create such an entangled state? So I know, let's see what we know. I know that I need 2 qubits, obviously. And I know that if I do this, sorry. I know that this will not work, right? Because, if this was the case, then there's no entanglement here, right? This is just a tensor product. If you call this state U1 and U2, right, the whole system is U1 tensor product U2. And I know that this state cannot be written as a tensor product of 1-qubit states, right? So there is no way this circuit will ever work, will ever allow me to create that state. So I need somehow to entangle. So how do I represent entanglement? So we have this concept of control gate, control operations, it's a control gate. So let me write as a CU, little c for control, which takes so U1 and U2, or let's say U in system A and V in system B. And this is defined as what? As U, A, B, sorry, B, if U is equal to 0 and U, A, U, V, B, if U is equal to 1. So what it means is, so CU is a control gate. So the first qubit, the U, acts as a control. And the operator, the unitary operator, acts on system B. So if the first qubit is in 0, then I don't do anything. This is just identity. And if the bit U is in 1, then I apply the operator, the unitary big U, to the 2 qubit V. And the representation would be like this. So let's say UA, VB, they have U. Like this, right? So the big dot here means the first one is a control and U, and the unitary U applied to the second one. Okay. So my claim, we're going to be, can I write? Oh, I can write here. My claim is that 0, what do I want to do? I want to do this. I apply Hadamard there. And then I do X. And then I do this. And then this is equal to psi. This is my claim. That my entangled state psi can be generated with this control circuit. Well, let's prove it or disprove it. Yes.
One silly question. So you're defining this operator U control, right?
Yes.
Okay, and as a linear operator, you have to define it in a basis, essentially.
Sorry?
As a linear operator, you have to define it on a basis, right? On a basis of this space. That is a tensor between the A guys and the B guys.
Yes, I mean, here all my system would be, all my Hilbert spaces are C to the 2n, 2 to the n.
Exactly. So I'm just looking at the definition, right? And you say if U is 0 or if U is 1.
Yeah, because if one qubit is 0 and 1, this is my basis.
Okay, so this means that you have these qubits, and then the first one looking as a control, and then the others receive the action of the U. Is that so?
Yeah.
Okay.
Yes.
That's the way you define
Yeah.
it. Okay. Thank you.
So hopefully the example will make it clear. So here, if we were to write it mathematically, okay, so what will we have? We would have 0, 0. So maybe let me use colors. Just like this. So first, I have Hadamard. Then, okay, here, sorry. Here I can say this is tensor product identity. Right, so this is this part. Yeah. And then I apply control X, which is control X. And again, if you go vertically, these are tensor product. Horizontally, this is multiplication. Matrix multiplication. So I have first part here, first operation, and then second operation. But of course, you can imagine as soon as I have quite a few gates and so on, this becomes quite ugly to write. As much as I like math formalism, sometimes it can look very ugly here. But let's do the computation, right? So let's call this psi 0, right? Which is after applying the Hadamard identity, and then so psi 0 is what? Well, psi 0 is, again, what we said, Hadamard identity applied to 0, 0. Sorry. Which is the same as Hadamard applied to 0. Tensor product identity applied to 0, which is, well, Hadamard applies to 0. This is 0 plus 1 over root 2. And then tensor product identity applied to 0. This is 0. So of course, this is just root 2, 0, 0 plus 1, 0. This is correct. This is not quite what I wanted here, right? But now I can apply control X. So now, I apply control X. So maybe, let me again use my color thing. I'm not erasing anything, I'm just changing the colors. Right. So what does it say? So control X, the red one is the control, and the black one is upon which the gate is act, right? So if the red one is in 0, so if UA is in 0, then it's just identity, nothing happens. Right? So the first one, so yeah, everything is linear, so I have the 1 over root 2, this one stays out. If red one is in 0, that's the control, I don't do anything. So I don't do anything. Plus. Now, if the control red one is in 1, then I apply X to the second qubit. X is the NOT gate, so if it's in, if it flips the qubit, qubit 0 becomes 1, qubit 1 becomes 0. There, the black one is in 0, so it becomes 1. But it does not change the control. Right? The one, so yeah. This is a plus, right? This bar is the left bar of the cat, right? And so this one has not changed. 1. This one, the 0, no, has been flipped to 1. But this is exactly the quantum state psi that we wanted to get. So this quantum circuit here it's entangled. The entanglement comes from the control, yeah, from the controlled operation, and that creates the entanglement, right? basically every quantum computation from now on are just extensions of this. So now, unless you have just a question, let me look at.
Sorry.
How does the entanglement work with larger vectors? That's the question, right?
Yes.
Well, you just add stuff.
Do you always take the first one to decide and then apply?
Oh, no. Okay, let me give you a more fancy example. I really want to be nasty as a home exercise. Let's say 4 qubits. Usually, I can do this. Adama. X. But maybe I can do this. Maybe not X, but I'll put Z now, I'll put another one. And maybe I entangle this one with this one. Let's say Y. You can have a lot of fun. So, oops. Home exercise, what's the quantum state? Sorry. Yeah, I'm not going to write it. But the point is, this is a general quantum circuit with four qubits and with loads of entanglements. So one important thing in this circuit, actually, there are two important things. One is all the operations I have, all my matrices, if you wish, are either 1 qubit or 2 qubit operations. I don't have 3 qubit operations, right? I don't have a gate like this, right? That acts on 3 qubits. Why? Because we don't know, physically, we're not able to implement this today. No quantum computer can do this. Quantum computers can do the black part, cannot do the red part for now. Second thing, so let's call them 1, 2, 3, 4. If I want to be able to implement this on the computer, it means, let's try to do this. It means I need to be able to connect 1 and 2, right? Because they are entangled. I need to connect 1 and 3, right? With this one. Maybe I can have a lot of fun with the colors. Red one. I can connect this one. That's 3 and 4. And blue. I connect 2 and 3. So it means I need a physical device that's able to connect the qubits like this. If this is my circuit, in fact, I don't need all the qubits to be all connected to each other. I don't need full connectivity. Because to implement this circuit, I don't need 1 to be connected to 4. Right? And this is very important, and we'll see that in a minute, because right now, if you have an n qubit, even 7 qubit quantum system, usually they're not fully connected. It's very hard to do full connectivity of all the qubits. But if this is a circuit, and a qubit, this circuit is enough for whatever you want to do, well, you don't need full connectivity.
And you can also go down.
Right?
So this control gate can also go down.
What do you mean?
In the sense that you only connect.
Oh, yeah, but this is just okay. Let's do. You just like me playing with So let's do 1 and 4. But I do like this.
Yeah. Thank you.
That's right. This is fun, actually. It doesn't matter. I mean, this is just a representation. But again, the 2 and the 4 are not connected directly. They're connected through 1 through, what did I say? 2 and 4 are connected through 1 through 3, but not directly.
Sorry.
Yes.
So if I understand correctly, you say that if I actually have a physical quantum computer right now,
Yes, and we do.
there could be some algorithms that I can actually implement with it, and some
Yes.
others that I cannot because
Yes.
of limitations like this.
Yes. Exactly.
Operations as possible.
It depends, actually. So, I mean, that's a very interesting question, and I think it depends how you position yourself. So, for example, should you write algorithms that are that are hardware dependent, or should you write general purpose algorithms? Yes. So, I'm going to switch to the computer now. That will hopefully answer these questions. First to state one thing: any quantum operation, that's the keyword to remember. Any quantum operations can be computed on a classical computer. Can be. The problem is when n goes large, 2 to the n is a big thing. If I think in terms of matrix, n is 20, 2 to the 20. Well, okay, let's even take 10. 2 to the 10, that's a 1000 by 1000 matrix. This is a fairly big matrix. I know, tensor network people, and not, can do that very efficiently, right? But this is still a big matrix. And of course, n is 10. This is not that much. The point is, if n is 100 qubits, this is a huge matrix. So yes, I can do matrix computation on my classical computer. The problem is you ultimately run out of memory. So that's one thing. Any quantum computation, and we'll see that on my not quantum laptop.
I did not explain myself. When I was talking to emulator, I was talking about emulator of operations, in the sense that, for example, you give a quantum computer something that is really maybe complicated and you cannot write it in an obvious way like this, but it has some kind of translator that would split it in small implementable operations.
I will show you.
No classical computer involved, essentially.
Yes. So yes. What's it called? Transpiler. So a transpiler says that if you, let's say 2 by 2 rotation gate, is going to convert to express. So let me state the lemma. Any U into 2C can be decomposed as U is, okay, something like this. Theta. I haven't explained this, but I will. So R Z or X of theta is defined like this: I minus I theta over 2Z. So this is a rotation of angle theta around the Z axis, basically. The point of this lemma says that if you give me any operator U and the unitary operator U, I can decompose it into Z and X, basically. Z and X can be physically implemented on the quantum computer. So this is, for example, so the examples I'll show later, this is using IBM Qiskit, IBM quantum computer. If you give IBM a U, which serves your purpose, it will first apply a transpiler, which is it will decompose it into quantum unitaries that can be implemented on their hardware, which I think was your question. So you cannot, in theory, this, in practice, yeah, so theta 1, theta 2, of course, they're between 0 and 2 pi at the angle. I can only do 2 pi k over n with some discretization, right? You don't have lasers in every possible, but yeah. But that's what the transpiler does. So, yes, so now we can look at some nice pictures. So let me first show you some pictures and then code. So, yes, I need to play with this. Stop sharing. There. Podium. Expert. Okay, so let me show you simple things first. This was, maybe I can make it bigger. This was very exciting. This was IBM quantum hardware, I think a few years ago, 4 or 5, I can't remember exactly, a few years ago. So this was a 5-qubit system. If you know, okay, it's not exactly the same, but the point is, you cannot have a circuit that directly entangles qubit 0 and qubit 4. Right? You can only have a circuit that connects, that entangles 0 and 1, 1 and 2, 1 and 3, 3 and 4, but not directly 0 and 3. Because having full connectivity of all the qubits is extremely hard. Usually what we can do now is do pairwise entanglement, but even so, not between all of them. So this, I can't remember, they all have birds' names in IBM. So I can't remember which one that was. That's one of them. That's another one. That was a 7-qubit. And again, you know, similar idea where I can do some pairwise entanglement, but I cannot connect, I cannot have a control gate between qubit 0 and qubit 4. I can probably, you know, transpiler emulate this by going through 1, 3, 5, but I cannot do it directly between 0 and 4. Here's another one. This was a 15-qubit. So there's a lot more connectivity, but not full connectivity either, right? You don't have all the diagonals and diagonals, for example. And the 7 is a bit left alone. What else did I want to show you? So, okay, let me show you this one. Okay, let's see. Anyone from the UK? Yeah. There's one guy. Yeah, but you're too young. Okay. Sorry? Well, it depends. You can make fun of the English. That's all right. You agree with me, right? So in the UK, there's been this thing. Maybe, you know, even if you're young, you know, the premium bond. The young people have no idea. Okay, I didn't know either before, right? I'm not. So the point is that was done a long time. it's been running for, I think, the past 30 years. Premium bond every year, not every year, actually, I think every 3 months, the government delivers bonds. There's a lottery, and it draws some random numbers. And basically, there's a premium to these bonds where if you get picked by the lottery, you get an extra bonus, basically. It's been running for, I think, 30 years. And it's quite popular. The big thing is, I think the gains, capital gains are tax-free, which is, of course, the important thing. Anyhow, so, of course, if you have just a few bonds that are emitted, this is fine, because random numbers are fairly easy to draw. But now the premium bonds have become a huge thing. Ask your parents. The 3 guys from the UK, ask your parents, I'm sure they know about it. I'm not giving any investment advice, right? But so the random number generator they've been using was called ERNIE, ERNIE. So the R and the N stands for random number, and the rest I can't remember. But in there've been, I think, the first ERNIE back in the 60s was, of course, a big machine and so on. In 2019, they bought this, well, fancier version of this, which, okay, there's a fancy version, but the point is you can buy this. So this is basically a quantum chip that does one thing only, which is to generate random numbers. And so this is to put, a little bit of practical thing, everything I've been saying. This is, there are some applications now, and they switch to, okay, certified by Swiss, right? So it has to be good. It has to be good, high quality. Sorry? Yeah. No, but that's that was a few years ago. So they actually bought. So they bought some. So ERNIE now, the random number generator is done by quantum chip. If you have a few Ks to spend, you can have this. Okay, I haven't bought it, right? But and it's not supported by Mac, right? But who cares about Mac? It's on Windows 10. So the point is, this serves one purpose and one purpose only, is to generate random numbers. This is one thing to bear in mind, is if a quantum computer, and we'll see different examples of applications, a quantum computer will never be a general purpose computer. It can be, and there are some theoretical proofs for that, in particular this, where it can be extremely powerful at performing some specific tasks, but not for general purpose things. Right? You're not going to start, using WhatsApp on your quantum computer, or Telegram, or whatever. So that's one thing. The other thing I want to show you 2 graphs. So one is about, we've seen qubits, right? They are kets or rays in helpless spaces, and not know physically what they are. How do I physically realize a qubit? How do I physically realize a quantum gate? So if you look at the news, you will see usually 3 keywords. So size, right? So a few years ago, regularly IBM says, oh, we have a new 1,000 qubit system and so on. This is, I don't know if you can see. Go back. Let me write them in big. Size, decoherence, and gate fidelity. Usually, well, most of the big headlines are all about size. But in fact, size is only one part of the story, and seemingly, especially in the near future, not the most important thing. Decoherence is extremely important. What it means is, so size is the number of qubits. right? And I should add, obviously, but it's related with connectivity. The connectivity we saw, right, is how, if you view it as a big matrix, how sparse it is, right? If I have 1,000 qubit, but there's no entanglement, then, it's, right? I need entanglement. So I need to be able to have some connectivity between the qubits. Decoherence means that if I perform operations on a qubit, after a while, the qubits will decohere, meaning there will be too much noise and it will not be accurate anymore. So I can only perform operations on a qubit for a certain number of time, after which it becomes pointless, useless. There's too much noise in the system. Everything we've said so far, this is for closed quantum system. Closed means there's no interaction with an environment, there's no noise. Well, tomorrow we'll spend a little bit of time at the end talking about noise and open quantum systems, which is what the physical reality is, but this we'll see that tomorrow. Right now we're talking about ideal quantum system, which are closed, so there's no noise from the environment. So in practice, what's implemented, there's a bit of noise in the system, meaning after a certain amount of time, the qubit is useless. Just 1 second. And gate fidelity is if I perform an operation, if I apply u to 0, I know that, well, if I apply x to 0, I start in 0, I apply x to 0, I have 1 with probability 1, right? But in fact, because it's not perfect, I probably have alpha 0 plus beta 1, but alpha is very close to 0, but it's not exactly 0, right? That's what gate fidelity means. Sorry.
Thank you. What is the order of time that we're talking about?
Give me a second. Patience. So these are the 4 keywords, right? Very important ones. Now, how do I physically realize a qubit? What's a qubit? So if you want to know the details, go take a physics class. I don't know. The point is there are several competing technologies realize qubits. So the big two are called superconducting qubits and ion traps, which are physical ways of realizing qubits. So we know that particles have this superposition property, where this has been tested in empirical proof that a certain number of particles that have this qubit property, which is they are in superposition of 2 states. And if I entangle them in some way, they are connected to each other. So you can think of entanglement as correlation if you wish, but it's not exactly correlation. Right? Why do I say this? So maybe I should have mentioned one thing. If you remember our state 0, 0 plus 1, 1 over square root 2, we said this is entangled state, right? Entangled means that if I perform an operation, if I measure the system, but I don't measure the whole system, I only measure 1 qubit. I only measure the first qubit. And I observe, so let's use colors again. I measure the first qubit, the red one. So I have basically I apply P0 tensor product identity, right? Then, and I observe 0, then it means I know exactly what the other qubit, in which state the other qubit is. Because if I observe 0 in the first qubit, then the other one has to be in 0, right? So this is entangled in the sense, if you have information on one, you have full information on the other, right? They are correlated, if you wish, but entangled. So now, how do you realize this physically? Well, there are several competing technologies. As I said, the big two are superconducting qubits, ion traps, and there are others. But and to answer your question and to put everything on the graph, this is this. So let's see. You see, leading technology So superconducting and ion traps, so trapped ion, and candidates. So NISQ means what? This is the important keyword, NISQ at the top right corner. This is noisy intermediate state, noisy intermediate scale quantum. Noisy because it's not perfect, and intermediate scale because it's not millions of qubits. Now, what's important here? So we have qubit lifetime. This is the decoherence. This is how long is my qubit valid for. Let's look at superconducting. And let's just look at the 50 microseconds. Let's ask question. Is that a long time or a short time? That's one answer. So to answer this, we need to look at the rest. Because, in fact, microsecond doesn't matter. The point is, what kind of computations, what kind of operations can I do during these 50 microseconds? In order to apply one gate, let's say the Z gate, so one quantum unitary, it takes 50 nanoseconds. To the 50 because it's easier, right? Meaning I can perform 1,000 operations. I can perform 1,000. I can have my qubit there. I can apply 1,000 quantum gates. These are called very deep circuits. For those of you who like neural networks, this is the exact same content. That's the depth of the circuit. Now the gate fidelity is, okay, every time I apply the gates, we said we're looking at closed systems, so there's no noise, but in fact, there's a bit of noise. And as I said, we'll see if we have time tomorrow at the end to talk a little bit about noise, which is, it's not 100%, right? There is a little bit of noise, so when I apply, if I start from gate 0 and apply the X gates, I know in theory I should get 1, but in fact I get alpha 0 plus beta 1, with beta being what? Being square root of 99.4%, because the probability is beta squared. And connectivity, nearest neighbors, right? Which is basically the examples I showed before, but so actually this one will not be possible, right? I will have basically this and maybe this one, but not, this was too much to ask. When the examples we had before, this is nearest neighbor, right? This is nearest neighbor. This is nearest neighbor as well. What else is important? Okay, blah, blah, blah. And so the big companies, IBM, Google, Alibaba, Rigetti. So Rigetti, right now they don't, so you have to be careful about the news. So I think it was in November or something, or December, IBM revealed a new quantum computer, which had like 100 or 200 qubits. And I think a week later, Rigetti announced a new 8-qubit system. So of course, on the face of it, it looks, oh, one is Goliath and the other one is David. But David wins, right? But the gate fidelity was much higher in Rigetti, and you can perform a lot more depth, right? So the gate operation time was actually better. So size is not all that matters. And scalability, meaning how many qubits can I use? There's no major roadblocks near term. So in principle, you could scale them as much as you want, in principle, right? So this is for superconducting. If you look at trapped ion, so you see trapped ion, qubit lifetime is a lot longer, 50 seconds. This is very long, 30 microseconds. Of course, gate operation time is a lot slower. You can perform more operations, but then it's very hard to scale. So you can do it with a few qubits, but it's scaling beyond many is difficult. So there's no, right now, there's no clear winner overall. think it also depends on what you're looking at. It depends on the computation you're trying to do. Maybe you don't need full-scale quantum computer. Maybe you can do some of the computation you want with few qubits, but you need a lot of connectivity, or with many qubits but not so much connectivity. And this is related to what we were saying. Should we? But then, of course, one positions itself as, I don't know how you position yourself, as a mathematician or data engineer or data scientist or whatever. Should we write algorithms that are hardware dependent? So I want to price an call options in Black-Scholes. Should I write one that fits this system, or should I write one general and then wait for IBM to build a quantum computer? I think it's important, and that's what I like about quantum computing in finance. In finance, because the finance industry is very dynamic, right? So I think that's the beauty of it. But it's the first time really I see where interdisciplinarity comes into the picture, because we need to talk to these people. We need to talk to IBM. We need to talk to Rigetti. We need to talk to all these people because they're building the thing. And it's exciting because we need the algorithms, because there are very few algorithms so far. We need the hardware, and both at the same time. One thing, can I go straight back to page 1 or not? See that? Oh, yeah, no. Okay. So if you remember page 1, I said, I will not talk in this course about quantum Monte Carlo, about Shor, Grover algorithm, because in fact, this Shor's algorithm, Grover's algorithm, essentially rely on what's called quantum Fourier transform, or some version of it, which require a lot of bits and full connectivity. So quantum Fourier transform, every quantum algorithm, you can write it as a quantum circuit. I'm not going to write it here, but basically it needs full connectivity. And this is very long term. So probably not within the next 10 years. So that's why I won't talk about it right now. What else is important here? And so, of course, there are others. Others are photonic, silicon-based, topological. I'm sure, depending on the university you're in, you go talk to people from. Usually, that would be in physics department and in materials, right? Because in materials they're actually building, silicon-based chips and so on. Talk to them, and you'll see, there'll be some groups working on that, depending. Some do superconducting. So in Imperial, we have a big group in photonic, for example, and in the materials department, they showed me the building. I didn't understand anything, but that looked really cool. So talk to the people in your university and the physics department, materials department. Ask them to show you what it looks like. This is actually very interesting. Okay, so that's the. Is there anything else below? The key properties, blah, blah, blah. No. Let me show you one more thing. This thing. So this is, I don't have any shares in IBM, right? But I'm using IBM mostly because they were really the first to, they started investing and trying to build quantum computer over the past 20 years. But for a long time, that was, not under the hood, but, without any output. And it really started recently that, this is really something. And I'll show you the code. We're using their framework. But that's their development roadmap. So, okay, that's a new one. So it's very complicated, but there's everything. So what's important here is that's the hardware. So you see they all have funny bird names. Falcon, hummingbird, eagle, osprey. If you don't know them, Kookaburra, I have no idea what that is. Cockatoo, some really cool names. Anyway, you see that's the size, right? So it was 5 qubits, and then now we run here, right? So we have 100 qubits. So now there's a big change in point of view, which is instead of being bigger ones, trying to do distributed quantum computing. So instead of building a huge 1,000 and 1,000 and 1,000 qubits, maybe I can do actually both parallel quantum computing and distributed quantum computing, and to separate the computation into different quantum chips. So this is, what this says basically. This and this and this and so on. Then where is it? So we are on here. So right now it's the order 100, but again, 100, remember, this is just about number of qubits, but it's not fully connected. There's decoherence, there's gate fidelity coming into the picture. And actually one of the big things that they're working on is what's called quantum error correction, which says, classically, if I have one bit of information and I want to send it a question, and there's a probability P of the bit of information being wrong, then I can send it to him 3 times, and that will increase the probability, right? This is simple probability computation. Right? So there is something similar, which is sending it several times, or to minimize the error. So quantum error correction is one of the big things right now from the computing point of view. So how much time do I have? Until 10 minutes. 10 minutes. Okay. Yeah, sorry, I had the, okay. So let me show you quickly the code to see how that works. Does it work? Yes, this is me. So I'm using, so this is Python, right? You all know Python, I guess. So I'm using Qiskit here. So Qiskit is IBM. Basically view it as, what TensorFlow is. TensorFlow is to Python and machine learning. This is what Qiskit is to Python and quantum computing. It's provided by IBM. It's free, right? We just pip install the Qiskit package, and Bob's your uncle. So where's that? Okay, that's my library. Here it works. That's easy, right? I can create my circuit, quantum circuit, 1 qubit. QC, I apply Hadamard, so H, so H. 0 is, that's the Python index, right? 2 qubits, label, first qubit, which is position 0, label 0. So this is QCH here, and I measure, and this is 2 draw, right? So what this is my qubit. I apply Hadamard. This has no influence. This is convenient just for visualization when we have a lot of operations to kind of separate. Qiskit puts it automatically, but it really bears no effect whatsoever. Then this is a nice measurement symbol, which is definitely not like a psi, Burton psi, but I measure, and then you see after measurement I have this double arrow, meaning this is classical. So this is the quantum circuit. This is the same as what I was drawing here. Let me go back to this one. To this one. Yes. So how do I run it? So this is not a quantum computer. I couldn't take it in the plane. Otherwise, I would. I don't have a quantum computer, right? But I can use an emulator or a simulator to run the quantum computations on my computer, which of course will run out of memory if I have too many qubits. Alternatively, I'll send you all the notebooks if you want. And it's not this. This one, there's a lot, blah, blah, blah. Later, you can run it on the actual quantum computer, but then it need to be connected to the internet, and you ping it to IBM, and we have access, I think, right now for free to up to 7 qubits. So you send it, it runs there, and you get the result back. But let me do it on a simulator right now. Sorry, that was on it. Yeah. So here, let me look at this. So this example is exactly the one we had there. I have 2 qubits, Hadamard, and then I measure. So again, if I measure the whole system, I will observe my quantum system will collapse to one state, right? 0, 0, or 0, 1, or 1, 0, or 1, 1. That doesn't tell me anything about the alpha, beta, and if I want to estimate them, I need to do Monte Carlo. So I run the experiment a million times, and or 500,000 times, and I observe this, right? So I observe the state 0, 0 in almost 25% of the time. Ideally, that will converge to 25%, of course, right? And of course, you can do it with many, right? And then you get loads of stuff. So that's one example. Now, let's go back to the basics. So I'll skip quite a bit of detail here because, sorry. But again, I'm very happy to send you all this. So this is just, this is like pictures, blah, blah, blah. So this we said, right? This is just a circuit. Let me skip all this. I'll just run them in case. So this, of course, this is the more interesting one, right? Where I have a lot of entanglement there. Whatever the circuit does, I don't care too much, right? Yeah, I have 2 qubits, a law of entanglement. The plus, this is the X gate. This is because the reason it's a plus, because in binary, if you had 0, 0, that if you have 2 qubits and this is the plus, right, that gives actually, that does the NOT gate, right? 0 and 0 gives 0, and 0 and 1 gives 1. Let me skip this. The one I want to, okay, let me show you 2 things that are very important, and I will open tomorrow. We have this. This is basically says that, similar to the lemma I had, which is any unitary can be decomposed into X and Z gates, basically. Now in Qiskit, there is this general, so it's called U. Yeah, this U with 3 parameters, X, Y, Z, which is phi theta lambda, which generates this, and this, in fact, I can write any rotation matrix in C2 like this. So in fact, Qiskit has this U matrix implemented, or at least a decomposition of it into simple gates. This transpiler thing we were talking about. And what's important in this picture is I can parameterize my gate with 3 parameters here. Just to open to tomorrow, this I can view it as a neural network with layers and hyperparameters. The output is a distribution over 2 to the 5 points, right? But I have parameters, hyperparameters that I can tune if I want to. Right. So we'll look at this quantum neural network tomorrow. But that's general idea. Right? I can parameterize my quantum circuit with hyperparameters that would basically play the roles of your hyperparameters in a neural network, and then I need to define a loss function and so on. But that's the idea. Okay, let me skip this. The one thing I want to show you this. So a circuit, again, for the analogy with neural network. So I have a circuit here, doesn't matter what, I mean, you see I just generated randomly the values, but there's a property, the width and depth, which kind of have a similarity with neural networks. And the depth of the circuit there. And of course, the depth, if you have a very deep circuit, that can be good. But on the other hand, it means the hardware needs to have a high gate fidelity. Because if you lose a lot after many gates, then of course the result is very noisy. Rigetti, for example, is pushing, I mean, their hardware works very well with the low depth. Now, theoretically, do we need big depth? Not clear yet. Well, I'll talk about these universal approximations. Yes, one thing for Raoul, this. This is a control Y gate. We know what this is. Y. I didn't talk about Y, so let me use Z. Actually, Y is a bit better here. Control Y. Y is whatever it was, right? But and it's control. So qubit 1 acts as a control, and you see I can even do it upside down. And Y applies to Q0. Y is actually not implemented in Qiskit. Control Y is not implemented. But I can use the transpiler and I can decompose it. What is actually implemented is this. So S is a native gate in Qiskit. Doesn't matter really what it is, but it's one native gate. And so every gate is decomposed. That's done under the hood, but that's what the transpiler does. But of course, it means that when you actually compute the depth of the circuit, this is not depth 1, right? This is actually depth 3. But okay, that's life, right? So here, for example, Hadamard usually is actually correspond to the U2, which is not a native gate, and the Z gate is a U1, and then you have plus is control X is control X, that's a native gate. Then I have the control Y here, and then the rest. The last one is the swap. Swaps the 2 qubits. The swap is not a native gate, but the swap can be written as Hadamard, control X, Hadamard. So the actual depth of the circuit is not 1, 2, 3, 4, 5, but it's 1, 2, 3, 4, 5, 6, 7, 8. Again, different architecture, different hardware will have slightly different native gates and so on. Right? I'm aware of time. Let me just see if there's anything important here. This we already said. And yeah, that's all for today. So what I'll do tomorrow, so now we have basically all the elements we need. So tomorrow I'll look at applications. So I'll look at optimization, basically quantum annealing and adiabatic quantum theory, and quantum machine learning. And I'll try to say a little bit about noise and open quantum systems. That's it. Thank you very much for your attention.